Good day everyone. Today I'm going to explain about stability analysis with root locus analysis. The learning objective after this lecture is students should be able to stabilize an open loop process with root locus analysis. There are three types of order in open loop unstable process taken from Leuben in process modeling, simulation, and control for chemical engineering. This three order is first order, second order, and third order. And for the transfer function, it's like given in equation 11.44, 11.46, and 11.48. Let's take in the first example from the third order open loop process. Given that G open loop is equal to 1.5 Kc over 2s plus 8 times s minus 1 times s plus 9. Now let's use Kc equal 1 as the first trial, and we can make the block diagram in Laplace domain using Simulink. Next, plot the root locus analysis using MATLAB, where s equal to transfer functions of s, g is in the G open loop given from the question, and we plot the root locus diagram of the G open loop. Then we get the root locus plot. This root locus plot is for the third order open loop process, where the second and first have a different type of diagram on the root locus. And then the second step is we simulate the block diagram in Simulink, where the Kc is equal 1. Then the response from the Simulink shows an unstable loop. Then the question is how to make the unstable loop become stable. First, let's review the root locus plot. When we click the root locus plot, we can get the value of the system, like the gain value, the pole, the damping, overshot, and frequency. This is the position of Kc, where Kc is equal 1, and the position is on the right side of the imaginary axis, where the imaginary axis is this y-axis. Then, if we want to stabilize the loop, we have to pick the gain value or the Kc that's located in the left side of the imaginary axis. This can cause the loop become stable. So when we look at the root locus plot again, then try to click on the coordinates that intersect the imaginary axis. There are three poles that intersect. The first one, second, and third pole. Where the first pole is reflect the third one, then it has the same Kc point, where the 0.0 coordinate have the different Kc point of 48.6, and the first and third pole have a number of 402 Kc. It can state that the Kc minimum of this question is 48.6 and the Kc maximum is 402 if we want to stabilize the open loop. So if we want to stabilize the open loop, we should pick a number of Kc between 48.6 until 402. Let's take an example. If we change the Kc equal 80, Then we make the block diagram and change the controller number from 1 to 80, and we run the Simulink. Then we got a stable open loop. So the first examples explain us on how to stabilize an unstable loop by root locus analysis from the third open loop process. And these are the second example from the second order open loop. Given that the GOL is equal Kc over s minus 1 times s plus 9. Let's use Kc equal 1 as the first trial again. And we can make the block diagram in Laplace domain. And after that, all the steps are the same, just like the first example. But let's just try it. Okay. The plot Locus analysis using MATLAB of the second order have a different diagram from the third order. The second order give a plus sign of a diagram. Then when we click for the Kc equal 1, it is on the right side of the imaginary diagram. Then we should check on whether the intersects in imaginary axis it is where the Kc is equal 9.46. So the Kc minimum for the second order open loop is 9.46. So if we want to stabilize the loop is by picking the number of Kc greater than 9.46. So just make Kc is equal to 15, because 15 is greater than 9.46, and we change the controller from 1 to 15, then we get a different graph of open loop is a stable graph from the Simulink. It's different from the first graph, which is a non-stable to stable by changing the number of Kc from 1 to 15. Let's look at the third example, is the first order open loop. Given that the G open loop is equal to Kc over 9 minus 2, and let's make the Kc is equal 1, just like the other example, and we can make again the Laplace domain block diagram, and we run again the plot root locus analysis using MATLAB, and we got the diagram of the first order is just a straight line. And we can know that the Kc equal 1 is on the right side of the imaginary axis, and we should just pick the point, the coordinates that is intersect the imaginary axis is on 2.03. So the Kc it should be greater than 2.03 if we want to make a stable loop. Then just take an example if Kc is equal 3, which is greater than 2.03, and we got a stable open loop. So the conclusion from this 3 example is we can know what is the minimum of Kc and maximum of Kc is from the root locus plot. That's all for today's explanation. Hope you guys understand the lecture, and have a great day, everybody.